Inference for distributions of categorical data. Now, we've already seen some inferences, so some inferential tests with categorical data when we did proportions. So we calculate proportions anytime we're working with categorical data. However, in this chapter, we're going to take what we did with proportions and we're going to expand it to a larger set of values. So with proportions, we could either do one simple set of data, look at the proportion for that one set, and then run a test or an interval from there. Or we could do two proportions and compare them, one to the other. How do they compare? Are they the same? Are they different? And so on. What we're going to be doing here is expanding to multiple different proportions. So there might be 5 or 6 or 10 proportions that we're looking at, and we want to be able to compare. Okay? So in section 11.1, we're going to be talking about the chi-square distribution, and then also we're going to talk about the goodness of fit test today. So the chi-square goodness of fit test. So up to this point, we have had two different distributions that we've primarily worked with when we've done our confidence intervals and our hypothesis tests. When we dealt with proportions, which distribution did we always use to calculate probabilities? So when we worked with proportions, what distribution were we able to use? The same distribution we've used all the way since second chapter, first semester. Starts with an N. Normal. Okay? So we use the normal distribution to calculate probabilities and p-values anytime we were working with proportions. So that's whether it was one proportion or two proportions. So we would calculate z, calculate the probability, that became our p-value. When we worked with means, so if we were working with means, either one mean or the difference of two means, which distribution did we use? The t distribution. Okay? And when we said t distribution, that was kind of a misnomer because the t distribution is actually what? So the normal distribution, the standard normal distribution is just one distribution. Regardless of what information we started off with, as soon as we standardize it, we're the same distribution regardless. Okay? But with a t distribution, what actually happened? Well, there's an infinite number of t distributions, right? Based on degrees of freedom, which we calculated using number of the sample size, right? So a t distribution was defined by the sample size used to create the data that we're working with. So the normal distribution, the standard normal, was the same distribution regardless. Didn't matter what sample size it was, didn't matter what our units of measure were, the normal distribution is the normal distribution. With a t distribution, it was an entire family of distributions. So there's an infinite number of t distributions based on sample size. Okay? Now the chi-square distribution is a third type. So this is a third distribution that we're going to work with to calculate p-values to determine whether we reject or fail to reject our null hypotheses. So we're going to be talking about running different hypothesis tests with these categorical variables. So we're going to start off with an example and just kind of work our way through it here. So Mars Incorporated makes milk chocolate candies. Here's what the company's Consumer Affairs Department says about the color distribution of its M&Ms. On average, the new mix of colors for M&Ms will contain 13% of each browns and reds, 14% yellow, 16% greens, 20% oranges, and 24% blues. Okay? Now, for this portion, as far as how the notes are going to go, I want you guys to copy these percentages down. So I want you to make like a little table. So you're going to have brown should be 13%, red should be 13%, and then yellow at 14, green at 16, and so on. So copy those percentages down into kind of like a little makeshift table in your notes here. It's going to make more sense if you have these in front of you as we go through the problem. Now, what I'm going to put up on the screen here, which you'll also want to just kind of get a copy down on, is a table that summarizes the distribution from a sample bag of M&Ms. So if we open a sample bag of M&Ms, this is the result when we counted the number of each color here. Okay? So in that bag of M&Ms, there were 9 blue, there were 8 orange, 12 green, and so on. So get those copied down. Now, something to be aware of here, when they gave us in the problem, when they reported the different colors, what did they give us with those colors? Percentages. What percent of the candy should be a specific color, right? Now, when they opened the bag of candies and counted up, they gave us counts. How many actual M&Ms were blue, how many actual were orange, and so on. So these are not percentages. Okay, it's not 9% were blue, 9 actual candies were blue. Okay, so the problem gave us values in percents. We got values in terms of counts, how many were actually in each one. And then it's important to recognize the total. So there were 60 total M&Ms in that particular bag of M&Ms. Okay, now if we were to compare just straight up color to color, how would I figure out the proportion of blue candies there are in this bag of M&Ms? So if I wanted to know what percent of my sample bag was blue, how would I do that? Yeah, just take the value divided by total. So we would take 9 divided by 60, and we'll get our percentage. Okay? So, based on our sample data, the sample proportion of blue M&Ms was 9 out of 60, which would be about 15%. So that's where the 0.15 is. So the sample proportion would be 0.15. Now, what did the company claim should happen? Should be at 24%, right? So when we look at this, initially, since they're claiming to have 24% blue candies, we might believe something's wrong. We might think that they're misrepresenting their information. So we could run a one-prop z-test. So a one-sample z-test for proportions to test the hypothesis. They claim to have 24% blues. We claim, based on our information, that that's not true. We claim that the proportion's not 24% like they claim. So we could very easily run that particular test. So we'd go into our calculator, type in our one-prop z-test, plug in the values we need, and we figure out whether they have the correct proportion or not. Okay, so that would be something we definitely could do. So we could do that. Whoops. But that only tells us the blue portion, right? So then what would we have to do next if we wanted to continue through that? We'd have to do orange, then we'd have to do green, then we'd have to do yellow. So we could run a one-prop z-test for every single color. But that's a lot of work, right? And the other thing is, if I'm trying to do this all at once, okay, what we're concerned with is the overall distribution of the bag. Does the overall distribution follow the distribution they claim? Okay? So by looking at each individually, first of all, we'd have a ton of work. Okay, we'd have to run a hypothesis test for every single color. Right? The other thing is, one sample z-tests won't tell us how likely it is to get a random sample of 60 candies with the same color distribution as what they claim. Okay? So running each one individually isn't going to tell us overall whether the distribution matches, whether the distribution is close enough to say it's the same or different enough to say that it's not. So, in order to do something like that, where we're looking at an entire distribution at once, we're going to use what's called our chi-square goodness of fit test. Okay? Now, as far as notation for this, you can always write out chi-square goodness of fit test when you tell me what test you're running, but chi-square is kind of just this notation here. It's just kind of, and you can just do a normal x squared, something like that, okay? But that's going to be like a capital X squared is your chi-squared, and then for goodness of fit, you can just call it GOF. So chi-square GOF test. So on a quiz or a test or in your homework, when it's time to say what test you're performing, you can write it out that way. Okay? So the chi-square goodness of fit test. Now, with the chi-square goodness of fit test, just like any other hypothesis test we've run until now, we have to have hypotheses. So the null hypothesis in a goodness of fit test will always be, that the reported distribution is correct. So the null hypothesis should state a claim about the distribution for a single categorical variable in a population of interest. So one of the things here to make sure, the goodness of fit test, to know that you need to run that, you are looking at one particular variable and you're looking at the distribution of that one particular variable. So it's one sample, one variable, and you're looking at the distribution of that one variable. So in our example here, our null hypothesis would be that the company's stated color distribution, so those percentages they reported to us, are correct. The null is always that the original is correct. Okay? Now, notice also with this, in our previous hypotheses, one of the things that we tried to get across to you guys is that these hypotheses are in fact statements. Okay? But with proportions and means, we were able to abbreviate those statements using notation. So we could have said P equals 0.24, but what that stood for was the true proportion of blue M&Ms in a bag of candy should be 24%. Okay? With chi-square tests, there's no notation to abbreviate. So when you write your hypotheses, they're actually going to be physical statements that you write out. Okay? The good news is that they're always going to be the same pretty much. So when you're looking at a goodness of fit test, you're just saying that the distribution reported is correct. You just have to put whatever context for that specific question's in there. Is everyone okay with that? So the distribution stated is correct. That's always our null. Which means our alternative would be that the stated distribution is not correct. So when we want to write our alternative hypothesis, it's that our variable in question does not have the specified distribution. So your null and all alternative hypotheses for a goodness of fit test should be identical, except one should say is correct at the end, the other one's going to say is not correct. So null is always assuming it's right, alternative is assuming it's wrong. Now, here's the other main difference between these types of tests and our previous tests. When we had our alternative hypothesis before, we had the option of less than, greater than, or not equal to, right? With a chi-square test, there's no way to determine whether anything's greater or less than, because if you think about what we're doing here, we're running a test over multiple different categories. So it's no longer one simple proportion that we're looking at. We're looking at 6 different proportions and how they all compare to each other at the same time. So there's no way to determine if the percentages are less than or greater than based on an overall look. So when you're looking at these alternative hypotheses for the chi-square test, they're always not equal to. They cannot be a greater than or less than. There's no direction to the difference. Okay? So, we okay with the hypotheses? Should be pretty straightforward. Just insert the context. This distribution is correct. This distribution is not correct. Okay? So it should be pretty straightforward. Now, the idea of a chi-square goodness of fit test is to test whether the observed counts. So when we actually take a sample, we're going to have a specific set of counts for our different categories. So do those observed counts match what we should expect to see within that sample? So one of the things to kind of be careful with here is when you're doing your goodness of fit test, your values need to be in terms of counts. How many objects are there? You will not use the percentages like they'll generally report within the problem. So that's something you might want to highlight or add into your notes there, is we are talking about counts. How do the observed counts compare to the expected counts? Now, as far as observed and expected counts go, these are pretty straightforward. The observed counts would be the ones you physically see within your sample. So in our problem, they would be the counts reported from that sample bag. So there were 8 blues and 9 whatevers and 16 whatevers and so on. So that's how many were actually physically in the bag that we opened. Now, they gave us a stated distribution at the beginning. And they said that all of our colors should form these different proportions. So if we take those proportions, we can use that to calculate how many we would expect to see in a bag of 60. So we opened a bag of 60 and we found exactly how many were in there for each color. Those are the observed counts. But we need to compare that to what we should have expected to see had it followed exactly the distribution that they claim. Okay? So to do that, you would go color by color and take the 60 M&Ms that we started with times the expected proportion. So for blue, we should expect to see 24% blue candies. So we had 60 in our bag times the 24% we should expect, and we should expect to see 14.4 candies on average. For orange, we should expect to see those 20% of the time, so 60 times 0.2, we should expect to see 12 orange candies in our bag. And then so on. We work each color out according to the stated distribution proportion. Okay? Now, notice when I calculate these expected values, I get 14.4, 9.6, 7.8. Okay? Is it okay to get decimals here? So if I was looking at an observed count, so when I actually open the bag and I physically count the number in each one, will I ever get decimals? No, I'm going to be counting whole M&Ms, right? But think about what we're calculating right here. We're calculating an expected number, right? This is an on average. So on average, if we opened up numerous candies, so if we opened up bag after bag after bag, on average, we should expect to see 14.4. On average, we should expect to see 12 orange, and so on. So when you calculate your expected counts, those can be decimals. Okay? So you want to keep at least a couple decimal places with each of those expected counts to make the calculations as accurate as possible. Everyone okay so far? So the observed accounts come from what you actually observed when you sampled. The expected is what's the average you should expect to see based on the stated distribution. So using your sample size, how many should you expect to see within that given scenario? Okay? So then what we want to do is create a table with both. So we want to know, how does our observed compare to our expected? So in our problems, and you don't have to copy this down because you have a table with these counts and you have a table with these counts now, so you can just use those to compare from there. In a normal problem, you would maybe want to organize in this fashion because it'll make it easier, especially when we get to the part where we talk about how to calculate in the calculator. So you would put your categories along the first column. How many did you observe? How many did you expect? So this would be the way you'd want to, as far as in your homework or on a test or quiz. Okay? But you don't have to reorganize it now because you already have all this information. So we observed 9 blue candies. We expect to see 14.4 on average. We saw 8 orange. We expect to see 12. We saw 12 greens. We expect to see 9.6. So if we look at it, should we expect that the observed matches the expected exactly? No. Since this was a sample, and a sample of only 60, which is fairly small when you think about the total number of M&Ms produced, right? We shouldn't expect to see everything match up exactly. So the fact that they're different doesn't necessarily mean that this distribution is different than this distribution. Because remember, we're not talking about individual values at a time anymore. We're looking at the whole distribution as an entire entity. So we need to see whether the observed distribution is close enough to the expected to say that their claim is fine. Or whether it's different enough to say their claim is wrong, those percentages need to be changed up a little bit. So they need to reevaluate and calculate some new percentages. That's the goal of what the test that we're running here is going to be. So, to run that test, we need to calculate what we call the chi-square statistic. Now, this is no different than when we had a normal distribution. We calculated a z-score. Any normal distribution that we worked with, we had a z-score, which we then calculated a p-value from that. When we worked with means, we had a t-distribution. And for that t-distribution, we calculated a t-score and calculated a p-value from that. So it's no different than any other test we've run. It's just now that we have a different test statistic. So in this case, we have a chi-square statistic. So the formula is really pretty straightforward. Take your observed value minus your expected value and square it. Why do we want to square? Think about how these observed versus expected will match up overall. Yeah, if we think about this, if I'm going to subtract, okay, sometimes I might get a negative number, sometimes I might get a positive number. If I don't get all positives here, what's probably going to happen if I add up all the differences? Probably go to 0, right? Which is not going to give us anything. So, when we take our observed minus our expected, we square it to get our positive values, and then we divide by the expected number. So it's observed minus expected squared divided by expected. Now we do that for each category. So we would take the blues, the oranges, the greens, the yellows, the reds, and the browns. And we would calculate an individual value for each of those categories. So if we look at the blue, observed 9 minus expected 14.4 squared divided by 14.4. And then the sigma notation here means adding, summation. So then we add the orange calculation. So the orange would be 8 minus 12 squared divided by 12, and so on. Now, as you're copying this down, I wouldn't worry about copying every single one down. Okay, once you get like the first two, you should have kind of the basic pattern, right? So try the first two and then just kind of like a dot, dot, dot. So continue that through for each of your categories. Okay? And then from here, you simply plug everything in your calculator. Now, you could try to do this all at once. So you could do one real long expression in your calculator. I would recommend that you do it piece by piece. So calculate the value for blue, 2.025. Calculate the value for orange, 1.333. For green, for yellow. So calculate each one individually, and then add everything up after that. Okay? Now when you do that, make sure you keep at least 3 significant decimal places. So make sure you're keeping at least 3 decimal places to try to make it as accurate as you possibly can. Okay? But when we work this out following the formula, we get a chi-square value of 10.180. So that's our overall value, 10.180. So that would be like if we were working with a normal distribution, that would be like a z-score of 1.6 or whatever. Okay, that's the same exact thing, the same exact idea, it's just this is working with the chi-square distribution instead. Okay, so in a problem, when you're asked to find the chi-square statistic for a given distribution, you need to have your list of observed values, your list of expected values, and then you run it through the formula, piece by piece, add everything up at the end. You okay with that idea? Okay. Now, before we get too much farther, we should probably talk about when we look at this chi-square distribution. So we found this chi-square value. So now we need to know what to do with it, right? And so we talked about when we had a z-score, how do we work with it to find the p-value? If we had a t-score, how do we work with it? And it was all based on the distribution. So a chi-square distribution, it's a family of distributions. So it's very similar to the t in that each sample size or each number of categories that you were working with will create a different chi-square distribution. So there are family distributions that only take on positive values. So chi-square values cannot ever be negative. With a normal distribution, we could get a z-score of negative 2.1. With a t distribution, we could get a t-score of negative 1.2. With chi-square, we cannot get negative values. They always have to be positive, and that's because in our calculation, we square those differences. So we're always going to have those positive values that we're working with. Okay? Now, each particular chi-square distribution, just like the t distribution, is specified by a degrees of freedom. Now, the chi-square test uses the formula for degrees of freedom as the number of categories minus 1. This is extremely important here. With the t distribution, we use the sample size minus 1 to create our degrees of freedom. In a chi-square distribution, we use the number of categories being evaluated minus 1. So if we think back to our example that we were just talking about, the M&Ms, our sample size was 60. We had 60 M&Ms within the bag that we evaluated. But that is of no use to us when we talk about degrees of freedom, because we want the number of categories. So how many different categories did we have in our example? How many different colors of M&Ms? 6. So if I wanted the degrees of freedom for our test that we were just running through, we would take the number of categories 6 minus 1. So we would have 5 degrees of freedom. Okay? So it's extremely important to make sure you note, so highlight or star or underline or whatever you need to do to make sure you know it is not sample size minus 1 any longer. When you're working chi-square, it's the number of categories minus 1. So that's what happens when we work with that goodness of fit test there. So if we take a look at what this chi-square distribution looks like, for a degree of freedom of 1, so if we only had 2 categories that we were working with, our degrees of freedom would be 1, we'd have basically a perfectly skewed right distribution. But as we continue to add more and more categories, which therefore leads to higher and higher degrees of freedom, we notice that it becomes less and less skewed. What do you suppose will eventually happen? Yeah, it'll eventually become symmetric, so fairly normal, right? So if we get high enough degrees of freedom, we're approximately normally distributed there. Okay? Now, for our purposes, if we're talking about the number of categories, is it likely that we're ever going to have enough categories being evaluated to get to that point? Probably not. Okay? If you're evaluating that many categories at one time, that's a lot of information for a given set. Okay? So we're going to be staying more down in the lower ranges here. So we're going to have that skewed right distribution. Okay? All right. So first thing, because this used to be 2 days, so I have 2 different days worth of notes set up. So copy this down because this is part of your assignment. So on a normal non-block day, this is where we would stop, give you guys some practice. Now these problems, this 1 through 4, all it is looking at your chi-square, or looking at a scenario with observed counts, expected counts, or being able to calculate the expected counts, and then being able to calculate the test statistics, calculate chi-square based on the information. So that's really what these 4 problems are going to be about. Okay? Continuing on here, we just kind of introduced the goodness of fit test. We started talking a little bit about it, what it looks like. We talked about the hypotheses, what they should look like, how to calculate the statistics. So what we want to do now is talk about how to run the whole thing. So what does this whole test look like when we start to finish, and so on. So if we want to run a test for whether an observed distribution matches a predicted distribution, so whether the 2 match up. So we're looking at one categorical variable and looking at whether its distribution matches another. I would maybe write that down because, as I said, the next couple tests that we run through on Thursday and Friday, they're all going to be very similar in nature. So a chi-square goodness of fit test tests whether the counts of one categorical variable matches the distribution predicted by a model. So another way of thinking of that, or being able to identify a goodness of fit test fairly easily, it is one sample with one variable. One sample with one variable. Okay. Now, when we want to run a goodness of fit test, there are 3 conditions we need to check. And these 3 conditions are very, very similar to all the other conditions that we've dealt with as far as proportions and means. So you notice that we have the random and 10% again. So random, the data has to come from a random sample or from a randomized experiment. The 10% says when we're sampling, and we're sampling without replacement, our sample size must be less than 10% of the population. So those are no different than what we had before. Now the other thing to note here is the random sample or randomized experiment. So if you're running an experiment you do not need the 10% condition. So one of the things that can save you a little bit of trouble on like the homework, quiz, and test, maybe a little time, if you notice that it's an experiment being run, you do not need the 10% condition. That's only if we're sampling from a finite population without replacement. Now, the last condition is one that's a little bit different than what we've seen before. It's called the large counts condition, which is exactly what we called the third condition for proportions. But this one's just slightly different. The large counts for proportions said the number of successes and the number of fails within a given scenario has to be at least 10. With a chi-square goodness of fit test, all of the expected counts must be larger than 5. Or must be at least 5, I'm sorry. So in order to check these conditions, the random and 10% should be pretty straightforward. They're going to tell you that information within the problem. But for the large counts condition to be checked, you actually have to calculate all of your expected counts. So you would need to go category by category and calculate those expected counts and verify that they are all at least 5. Okay? Once you verify that they're all at least 5, then you can proceed with the rest of the test. Everyone okay with that? So be aware here, we're switching up the number that we compare to. It's now 5, and it needs to be those expected counts that have to be at least 5. And that might be something you highlight or underline in your notes, because one of the things that I notice that people do a lot, you might get a distribution, and the observed values might be less than 5. So you might have some cells where the observed counts are less than 5. You need to make sure that when you check this condition, you're examining the expected. The observed can be whatever. The expected, though, have to be at least 5. Okay? So, don't try to write all this down. Okay? A lot of this is stuff we've already talked about. So first, if the conditions are met, to determine whether our observed distribution does in fact match the predicted distribution, we would run a chi-square goodness of fit test. So the hypotheses we've already written down. The null is that the stated distribution is correct. The alternative, the stated distribution is not correct. And then you just have to put whatever context in there to make sure they know what they're talking about. We already talked about how to find the chi-square statistic. So once we have the null and alternative hypotheses written out, we should have the observed and expected counts written out. We would have checked our conditions, which would have been met. Then we calculate observed minus expected squared divided by expected for each of our cells. Add them all together, we get our chi-square. Once we know the chi-square value, here's the part you probably do want to make sure you write down. So if we have k different categories, so however many categories happen to be in this specific problem, the p-value, that's the piece we definitely want to make sure we get to. The p-value will be the area to the right of the chi-square value. So the p-value will be the area to the right of the chi-square statistic under a chi-square distribution with k minus 1 degrees of freedom. So the number of categories minus 1. So this is another difference between the chi-square test and any other test that we've written before. Before we could do a less than, we could do a greater than, or a double, 2 tails. With a chi-square test, it is always the area to the right, which when we come back from lunch, we'll talk about how to calculate the p-value on your calculator. It makes it a lot easier as far as putting in the parameters, because the lower, upper, and degrees of freedom all stay the same all the way throughout. Okay? So go ahead and head to lunch. start with your hypotheses, just like always. So the stated distribution is correct versus the stated distribution is not correct. You would check your conditions. Part of checking your conditions would be calculating those expected counts, and then calculate your chi-square statistic, plug it into the calculator to find your p-value, and then based on the p-value, you will either reject the null or fail to reject the null. Okay? So that's kind of the main idea behind what we're looking at here. So here's an example. In his book, Outliers, Malcolm Gladwell suggests that hockey players' birth month has a big influence on his chance to make it to the highest levels of the game. To see if birth date is related to success, which is judged by whether a player makes it into the NHL, a random sample of 80 National Hockey League players from a recent season was selected and their birthdays were recorded. The one-way table below summarizes the data on birthdays for these 80 players. Do these data give convincing evidence that the birthdays of all NHL players are evenly distributed among the 4 quarters of the year? So they split the year into 4 quarters. The expected distribution would be that they're evenly distributed. So there's no difference between how many hockey players there are and or where the hockey players are born and whether they are in the NHL or not. Okay? So that's kind of what we're looking at here. So first thing, we check write our hypotheses, check our conditions. So the hypotheses, our null hypothesis, would be that the birthdays of all NHL players are evenly distributed among the 4 quarters. Okay? So they were saying, is there any evidence to suggest that they're not evenly distributed? So the null is that they are evenly distributed. The alternative then, the birthdays of all NHL players are not evenly distributed among the 4 quarters of the year. Okay? So once we've written our hypotheses, next we check our conditions. So for the random condition, it did say a random sample of NHL players. 80 players would be less than 10% of all NHL hockey players. And then for the large counts, here's where you have to think about your hypotheses. So a lot of times the hypotheses will give you an idea of those expected counts. So if we have an equal distribution across the 4 quarters, then that means each of the quarters should have the same amount of players born within that 3-month period. So if we had our sample size of 80, if it's evenly distributed, there should be a quarter of the players born in the quarter 1, a quarter in quarter 2, and so on. So we take 80 times 1/4, all of our expected counts would be 20. Does everyone understand that? Okay. If we weren't going for an even distribution here, they would have had to somewhere in the problem say, we expect 20% of people to be born in quarter 1, 30% in quarter 2, and so on, in which case you'd have to calculate each individual expected count to find or check this condition. But since they all should be the same, we just do it once, we know what all our expected counts are. Okay? So, since 20 is greater than or equal to 5, we're able to proceed with our test. So, when we want to run our test, we calculate our chi-square statistic. So, in order to do that, we follow the formula here. Now, we just said all of the expected counts are 20. So when we subtract here, we're going to be subtracting from 20 and then dividing by 20 because that's the expected count for each quarter. The only thing we have to fill in is the different observed values. So for quarter 1, there were 32 hockey players born. So 32 minus 20 over 20, or 32 minus 20 squared over 20, and so on. So you plug each of these into your calculator, get a specific value, and then overall, we get a chi-square value of 11.2. So, go ahead and get out your calculator, because I want to show you what to do with this value now. So up to this point, it's just a matter of basic, take a formula, plug it in. Okay? Now the chi-square distribution, we said that the p-value is always the area to the right of the chi-square statistic. Okay? So, if our chi-square statistic is 11.2, we want to calculate the p-value associated with that particular statistic. So, in your distribution menu, so in second bars, if you scroll down, kind of towards the bottom, you should see a chi-square. So you see chi-square PDF, chi-square CDF. For our purposes, we always want the chi-square CDF. So for most of you, that would be option 8. So select your chi-square CDF. Now, from here, it's going to be very similar to when we did normal CDF or TCDF. It's the same process. We need a lower bound, we need an upper bound, we need degrees of freedom, and then we paste and it'll calculate. Now in this case, since the chi-square distribution, we always go to the right, what will always be our lower bound? Yeah, if we're always going to go to the right, so this is one where we never go left, okay? The only thing we're concerned with is what's greater than our particular value that we found, okay? So that means in every situation, every time you run a chi-square test, and you want to use your chi-square CDF function, your lower bound will be your chi-square statistic. So in this case, we would plug in 11.2 for that lower bound. And then if you're one with the menu, you just go to, or hit enter, go to your upper bound. If you're one that it just gives you the function on the screen, you hit a comma, and then you type in your upper bound. Now since we're always talking about greater than, so we're always going up to positive infinity, what's our upper bound always going to be? 1e to the 99. So you type in that 1e to the 99. And then the only other thing we need is degrees of freedom. So how do we do the degrees of freedom for a goodness of fit test? Number of categories minus 1. So if we think back to our problem, how many categories did we have? 4. So we broke it up into quarters, right? So there were 4 categories, which means our degrees of freedom would be 3. So let's say 11.2, 1 to the 99, 3, and then paste and hit enter. Okay. So on these types of problems, when you're working the chi-square CDF function on your calculator, the lower bound will always be your chi-square value. The upper bound will always be 1e to the 99, and then the degrees of freedom is just something you have to calculate each time. Okay. So what we just calculated there is our p-value. So our chi-square statistic came from our formula to find chi-square. We plugged it into our calculator to get a p-value. So if our p-value is 0.01, what would we most likely conclude? Reject the null. We didn't specify an alpha level at the beginning, which means we assume 0.05. So we just go with the safe bet of 0.05. So, since p is less than alpha, we reject the null hypothesis. What this means is we found convincing evidence that the birthdays of NHL hockey players are not evenly distributed among the 4 quarters of the year. So remember, when you're making your conclusion, it's always based on the alternative. So when we reject the null, we found convincing evidence to support the alternative. If our p-value had been larger than 0.05, we would fail to reject the null, so we would say there is no evidence to suggest that the birthdays are different within the different quarters, or they are not equally distributed or not evenly distributed among the different quarters. So we either find convincing evidence that the alternative is good to go, or we don't find convincing evidence for the alternative. Okay with that? Okay. Then, just a couple of things here to finish up. The chi-square statistic is only utilized with testing hypotheses. We will not construct any confidence intervals when it comes to chi-square values. So the three tests we're going to learn in this chapter, none of those are going to correlate to a confidence interval. We can only run hypothesis tests when we're working with chi-square. Okay, so that's one thing. A second thing, if the observed counts don't match the expected, then that means our statistic was too large. With a chi-square value, there is no such thing as too small. Okay, so it's always a large value that leads us to reject the null based on our distribution. Because again, we can only work with our positive values. So that value will always be large if we're going to be rejecting. So, the other thing to make sure we know is the chi-square test is always one-sided. If the calculated statistic value is large enough, we will reject the null. So it's always to the right. We can never work one to the left because we can't work with negatives. And then the last one, if you reject the null, there is no direction to that rejection. So there's no saying that this distribution was larger or smaller than the expected distribution. Because what we're looking at are individual values within overall. So all we know is that the distribution we observed is different than the observation we would expect to see. Okay? And it was a big enough difference that we would be able to say that the was rejected. Okay with that? All right, last thing. I want to go back to that last slide here. One of the things it's going to ask you to do in your homework. So it's going to ask you to run the test. So when you get to that point, it's going to say, do these data give convincing evidence that something is different than what we expect, type of thing. Okay? So you're going to run the test just like we showed you here. But what it's going to ask you to do is, if you reject the null. So if you actually find evidence to reject the null in favor of the alternative, they're going to ask you to do what's called further analysis. And basically what they're asking you to do is examine individually which pieces are causing the issue. So if we're looking at the distributions overall, some of the categories might match up really well. But other categories are going to be very different from one another. We want to know which categories are causing the issue. So which categories don't align themselves with the others. Okay? So to do that, you would have already calculated each of these individual pieces here. Okay? So in your calculators, I want you to calculate these for me real quick. So you guys calculate this first one with 32. These two rows, you guys do the 20. Well, that one's 0. You guys do this one, and then you guys do this one. So calculate the different values here. What did you guys get for yours?
7.2.
All agree there. What did you guys get for yours? Point what? 0.8. And what did you guys get? Okay. So, if in this case we know that we rejected the null because our p-value was less than alpha, so they would ask you to do further analysis. So the distribution is different. Where is it different? So where are we seeing the biggest differences among the observed and expected counts? So basically they're asking you to go back and look for the highest components of the calculations. So in this case, which one actually gave us the biggest difference? the first quarter. So this was quarter 1, quarter 2, quarter 3, and quarter 4. So this quarter 1 had the biggest discrepancy in it, right? And which direction was that discrepancy? So here we actually can determine a direction because here was our observed number of players born. Here's how many we expected to have been born in that first quarter. So it has the highest component for the chi-square statistic, but in which direction? Was it higher than expected or lower than expected? Higher. There were 12 more hockey players born in quarter 1 than we expect based on our original distribution. Okay? If we wanted to go a couple, so like sometimes you might have a couple that are pretty high contributors. So the other one would be our 3.2, quarter 4. And what do we notice about quarter 4 as it pertains to its contribution? It's quite a bit lower than expected. There were much fewer NHL players born during quarter 4 than we expected to see based on our original distribution. Okay? So if we notice, the middle 2 quarters actually kind of matched up pretty well, right? 0 and 0.8, those aren't going to contribute much to the overall calculation. But quarter 1 and quarter 4 differed pretty greatly. So this one had way more than we expected to see, this one had less than we expected to see. So when you're doing this type of problem and they say do further analysis, that's what they're asking you to do. Find those highest values, those highest differences, and tell which direction they are. So here we find something that's more than expected, here we find something that's less than expected, but they gave the most strength to the chi-square statistic. We okay with that? All right. Then, here's the other part of your assignment.
We can just do it all in one page. Or...
Yeah, you can do it all as one.